So we finished up talking about how to use the rational root theorem and then Descartes' theorem. There's also the upper bound and lower bound theorem for your possible roots. I'm not going to go into too much of that, so you can take a read on that to see how you can find upper and lower bounds for your roots. And then instead, I want to move immediately and kind of revert back to 1.6. And the reason why I'm reverting back to 1.6, this is going to be titled complex. I'm going to zoom out for a bit to make it seem nicer. Complex numbers. This is 1.6. I'm going to cover 1.6 and 3.5, and mainly because previously we have talked a lot about our functions, polynomials in the domain of real numbers. Well, it turns out there is a space or set of numbers that we're going to work with that's even bigger than the real numbers themselves, and they're called complex number. To give you a visual idea of what this is imagine this as your real numbers. The complex numbers system is bigger than that. This is the notation. See with that little slash on it. The complex numbers is all of your real numbers and more. It's the idea of, hey, you might have a red car or a red Honda as a real number, but then a complex number would be red cars in general. So there's much more. Now, complex numbers. So we need to cover a few definitions with complex numbers. The first definition I want to work with is this notation, this symbol denoted as I. This symbol represents imaginary numbers. This is your imaginary numbers. Imaginary number. Now, the definition I will give you guys is, the book gives you it as I is equal to square root negative 1. That's the definition of this notation. I, however, use the definition I squared equals negative 1. You can choose which definition you prefer more. One of them might be more flexible than the other. So pick and choose. This is the definition I like to use. This is the definition the book uses. And you'll see why I like to use that later down the road. So what is the complex number system? The complex number system, so if I showed you this set right here, complex number, all of it is just real numbers, union, that means combined, with imaginary numbers. Imaginary. That's all it is. The real numbers with imaginary. So the next definition we're going to go with is what is a complex number. Because we talked about imaginary numbers. I gave you the definition is just I equals square root of negative 1, or I squared equals negative 1. Now let's go with a complex number. Definition. A complex number. A complex number is in the form of a plus bi, and in particular a and b are real numbers. So these values could be 3, they could be values 2.6, 2.8, negative 4, 3 halves, square root 8. Those are all real numbers, so these could be values for a and b. Now, do not get confused with them being real numbers at what their component represents. So what I mean by that is A represents the real component of a complex number. The B, on the other hand, represents the imaginary component. A complex number is made up of a real component and an imaginary component. Now, these components are real numbers at the end of the day, but we need to make sure what they belong to for your complex number. Remember, it's going to be the real numbers union your imaginaries. That's where this is coming from. Understand? So, let's give some examples so we can identify what the real component is and what the imaginary component is. So, let's take negative 2 plus 3i. Well, the real component is negative 2. The imaginary component is 3. It is not 3i. 3i is an imaginary number. 3i is an imaginary number, but the imaginary component of this complex number is 3. So it's more so you got to be careful with your diction component. And this is the real component. Okay, so we got the idea so far. What about another example? Let's say I give instead negative 5i. Well, in this case, your real component equals 0. The real component is 0 because it doesn't show up. And remember, it's in this form at the end of the day. It'll always be in this form for complex numbers. So there needs to be a real component value, which is 0. And the imaginary component is not negative 5i, it's just negative 5. So it's not too bad so far. Now let's take another example. Remember, this is an imaginary number. Let's take another example, negative 4. Negative 4. We know this is a real number, but this is also a complex number because from over here in our image, all real numbers are complex numbers. So at the end of the day, I can treat negative 4 as a complex number. If I treat it as a complex number, the real value is clearly negative 4, but the imaginary value is 0. So you can write this as, you can treat this as negative 4 plus 0i. You can treat it the same way, but 0 times any value, 0 times I would be 0. That's why it's deleted in that case. Similarly, over here, this is just 0 plus negative 5i. The 0 is deleted for the real portion. So that's how you want to think about it. All right? This is an imaginary number. Negative 5i is an imaginary number. And this one is a real number. And a complex number is the combination of both. Now, they could be zeroed out, but it's a combination of your real and imaginary number system. So, imaginary numbers and complex number play a strange role because with the complex number, they make the real numbers so-called complete. Our algebra system is complete thanks to it, so we can do some sort of algebra that we couldn't do with real numbers. However, the problem with complex numbers is that we had to sacrifice something to gain that completeness. What we sacrificed was order. You can easily tell me that 5 is bigger than 4. You can easily tell me that. But let's take z to be a complex number and let's let this be, let's let the z value, I'm denoting z to be complex number. Why is it not erasing? Like this. Let's let z be the number, I don't know, negative 3 plus 2i. And then let's let w equal, these are complex numbers. W equals 4 minus 5i, or let me do just I. You can't tell me which one is smaller than the other with complex number. Is z bigger than w? Is w bigger than z? Because if I look at the real component, w has a larger real component. If I look at z, z has a larger imaginary component. So which one is bigger? You can't make that distinction. There is no way you can imbue an order on the complex number system. Now, somebody has created something called the lexicon order system, but that still does not solve the idea of ordering itself. You can calculate the norm, which is the distance that we'll talk about in calculus, but that's all you can really do. So, there's no ordering on that. We have to sacrifice that, unfortunately. Now, we got to talk about operations on these complex numbers. So the first operation I want to work with is equals. When are two complex numbers equal to one another? Well, clearly these two are not equal. Why do we not think they're equal? Well, the real component does not match up, and their imaginary component does not match up. So they're equal when, this is operation and complex. They are equal when real component are equal and imaginary components are equal. That means if I have two complex number, let's say I have a plus bi as one complex number. Now, let's suppose we have another complex number. Let's call it c plus di. They're only equal if, and only if, a is equal to c and b is equal to d. That is the only time they're equal. You need these two to be satisfied. All right. Now, that covers equal, so that's intuitive. Now let's go into addition. Addition should also be very intuitive. How do I add these two together right here? Negative 3 plus 2y plus 4 minus I. Well, the issue is that with these imaginaries and real numbers, when you're talking about addition and everything, they don't play the same way. They're two different objects. And because they're two different objects, I can't really combine them together. It's like apples to orange. If I say what's an apple plus an orange, you can't combine it together. You just say apple plus orange. However, there are some objects, parts of the complex number, that have the same properties. So in particular with addition, if I have a plus bi plus c plus di, I can actually add the real components together and add the imaginary components together. So this is the same as saying a plus c. This is the real components, real component. And this is why I need to know what the components are. And then you're just going to tackle on your imaginary component. This is your imaginary. Your real components and your imaginary components. Whatever's attached to your I, that's your imaginary component, the coefficient for I in particular. So that covers for addition. I'm going to leave subtraction as an exercise for you guys to think about it. I think that's, we talked about subtraction enough to know that, hey, we can deal with subtraction because it's the inverse of addition. Now, we go on multiplication. That's when it gets a little tricky. And I'm going to be very careful on my language here, but a plus bi times c plus di. So when you initially think about how to multiply, let's say we wanted to multiply 2 plus 3i times 3 minus 4i. Let's say I want to multiply these two complex numbers out. Let's call it a z. Let's call it as w. I want to multiply z times w. What does that equal to if I multiply these two out? Well, some of you guys might say FOIL. And foiling isn't the actual thing that's happening, but you can treat it like foiling. So what I mean by that, we define the multiplication as a times c minus b times d. That's going to be the real components. So the real component of our product is a times c minus b times d. That's going to be the real components multiplied, subtracted by the product of the imaginary components. That's going to be the real portion of our product. And then to do the imaginary component of our product, that's going to be plus AD plus BC of I. The imaginary component is simply the first real times the imaginary on the second term, and then or second complex number, and then it's going to be the imaginary component times the first real or the real number on the second complex number. Now, even though it behaves like this, you can treat it like foiling or distributing because it has the same property. It's not exactly the same, but they are equivalent mathematically or algebraically more so. So, for instance, let's verify that real quick. Let's actually FOIL this out together. If I were to FOIL out this value right here, well, foiling says I multiply first, outside, inside, or inside, then last. So let me do inside, then last. If I do that, I get 2 times 3. And then I'm going to get minus or minus 2 or times 4i. And then, let me erase this. Let me make this more clear. Plus 2 times negative 4i. And then plus 3i times 3. This is foiling. I'm just writing it all out. Plus 3i times negative 4i. And if you calculate this out, this is going to be 6 minus 8i plus 9i. And then minus 12i squared. Well, if I combine like terms, I have 6 plus I minus 12i squared. The definition I gave for I squared, this is the reason why I made, or I wanted to use this definition instead. I'm not going to say I made it because I didn't. But negative 12 times negative 1. I squared is equal to negative 1 from the definition earlier. And then we can actually calculate that out. That's 6 plus I times, oh, sorry about that. Plus 12, which is the same thing as saying 18 plus I. This is our product. This is what happens when we multiply two complex numbers together. We get a new complex number, 18 plus I. Now, this is by foiling. Now, if I go back by the definition, however, this should actually be equal to, let's do the real component first. So first, we're going to multiply the reals with the reals, subtracted by the imaginaries with the imaginaries. So this is 3 times 2, subtracted by the imaginaries multiplied, which is 3 times negative 4. This is the real portion. And then this is going to be plus. And then now I'm going to do the real with the imaginaries together. So I have 2 times negative 4. And this is going to be plus. Instead of minus, is plus now. 3 times oops, 3, yes, 3 times 3 I. Notice that I didn't have to include the I for this definition at all until the very end. All of these are just the coefficients I'm working with if I want to go by definition. Whereas if I FOIL it out, I have to actually calculate I into my work. Over here, I does not play a role until I write the imaginary components. So this is going to be 9 minus, what is that, negative 12? This is the real. We've already have the real. We don't have to worry about anything. They're not going to mess with each other. We're treating as different objects. Then this is negative 8 plus 9i, which is exactly going to be 9 plus 12. Oops, why did I say 9? It's supposed to be 6. I apologize. 6 plus 12. Plus, and then this is negative 1i. That's 18 minus I. Oops, is it 18? No, it's 18 plus I. I apologize. But yep, now if you see, they are the exact same. So, you can do foiling or you can go by definitions. At times, foiling might be easier, is more intuitive, but at times you might need to go by definitions. It's just fortunate it's not actually foiling, but it does give you the same results just because it behaves very similar to foiling. Alright, so that covers multiplication in particular, and I leave it as an exercise for you guys to try out this one right here. I want you guys to try negative 2 plus 3i times 3 minus 4i. You can try that out. So moving on. Leave it here for a bit. Now we go into division. Division is a weird one, but we have handled division similar to this kind of division. So let's say I have a plus bi over c minus d, or c plus di. Let's say I'm dividing two complex numbers. Complex number 1 is on a numerator. Complex number 2 is on a denominator. This means division. Remember that. If I treat it as a fraction. Or if I don't treat it as a fraction. Well, if I treat it as a fraction, we can actually, this is actually very similar to the idea of rationalizing.
If we remember from rationalizing, I had something like 1 plus square root 2 over 2 plus square root 3. Well, let's just say 1. If I had this case right here, I didn't like the square root. So instead, what I did to this problem to rationalize it, I multiplied the numerator by 2 minus square root 3 and the denominator by 2 minus square root 3. And the reason why I did that was so I can get rid of the square root at the denominator, and I'm not changing the value of the problem because this is technically multiplying by 1. So I'm going to do the exact same process with this guy. If I treat it like a fraction, which a division is just a fraction, I can treat this as a plus bi over c plus di, all multiplying by, because I don't want to change the value, c minus di, c minus di. This should get rid of the imaginaries for my denominator. It should. Similarly, like how we got rid of our square roots in our denominator, this should get rid of our denominators. So let's actually calculate that out. If I calculate that out, well, we have to multiply the numerator and we have to multiply the denominator. So you can check this by foiling, or you can check this by whatever method or the definition itself. So I'm just going to do foiling just so you guys can get the hang of it, because that's going to be a good way just to check if your answers are correct or not in case you forget some of the, I guess, definition parts. So if I FOIL this together, I get, for the numerator, I get AC minus A times DI, and then plus BCI, and then it's going to be minus BDI squared. All over, and all I did was distribute it. If I distribute my denominator, I get C squared minus CDI plus CDI. Oh, let me rearrange it so you guys aren't confused so far, because you might get confused here. DCI. I put the I at the very end. I just organized that. And then minus D squared, I squared. Well, I can simplify all of this together. At the very top, right here, there's not much I can do to simplify it. However, I know that I squared is negative 1. So let's use that definition that we worked with. If I use that definition, I get AC minus ADI plus BCI minus BD of negative 1. All over. Now for my denominator, I'm going to use the exact same definition. And if you notice, these two are actually like terms. They're all multiplication in those terms. So that means I can rearrange it. Multiplication is commutative. So CDI is the same thing as DCI in that sense. They're still like terms. I can combine them together. If I combine them together, they actually get deleted, believe it or not. Because this is negative, this is positive. So I get C squared minus D squared, and then I squared is negative 1. So we've created this, we're using this idea of rationalizing, but in this time was for complex numbers, so that we can actually calculate division. This is how we're defining division in particular. So I have AC minus ADI plus BCI, and then negative times a negative is a positive, BD, all over C squared plus D squared. Plus D squared. Negative times a negative is a positive. Well, we're almost done. Now, I like to just move all the reals with the reals, imaginary with the imaginaries. So I can see this as, this is a real component, and this is a real number, and this is another real number. Let's separate the reals with the imaginaries. If I do that, I have a new complex number on my numerator. It's going to be AC plus BD. That's my real component of my new complex number. And then it's going to be, in particular, well, I can do it multiple ways, plus BC minus AD of I. I just rearrange, I put AD second rather than first. All over C squared plus D squared. So this is how we're defining division. And if that is confusing, you can treat it as just rationalizing. That makes the problem much, much easier to work with. So let's try a problem out together. So example for division, it might seem confusing, but it actually isn't. We just need some arbitrary way to just show how it works. And if you ever get stuck, you can use this idea. So let's say I wanted to divide 3 plus 5i divided by 1 minus 2i. Let's say I wanted to divide these two together. Well, this is the same as saying 3 plus 5i divided by 1 minus 2i. It's the exact same thing. Nothing changed. All I did was just put this in the division symbol that I can work with. In rational expressions, we did the reverse. We always went with this way rather than this way. But now I'm turning into this method. So now I can multiply by its, we call it conjugate, and I'll define that in a bit. We can multiply both of them by 1 minus 2y, or 1 plus 2y, 1 plus 2y. And the reason is because I want to get rid of the imaginary number on the denominator. That is the whole point. So if I do this now, I get, let's see, for my numerator, I get 3 plus 6i plus 5i plus 10i squared. I'm distributing it out. Boom, boom, and then boom, boom. And then my denominator, I'm going to get, what is that, 1 or plus 2i minus 2i and then minus 4i squared. And the reason why you always get rid of your imaginary numbers multiplying by rationalizing it this way is because you're going to get I squared, which will get deleted. And then the middle terms will get deleted because they're just positive and negatives of themselves. So now for my numerator, I have 3 plus 6i plus 5i plus 10 times negative 1. I'm just using my definition. All over, well, these two cancel out. They're like terms. So now I have 1 minus 4 times negative 1. Now I get exactly, let's actually separate them out now. So this is going to be negative 10, 3 plus 10 times, or negative 10, I'm sorry, minus 10 plus 11i all over 1 minus, that multiplied each other, so that's going to be 1 plus 4. Then we have negative 7 plus 11i, my real and imaginary, all over 5. And then if you wanted to even simplify it even more, if you wanted to treat this as just one complex number, because this right now is not a, you can't view this as a complex number. However, if you actually divide it out, you can write this as 7/5 plus 11/5 of I, where this is your imaginary component, this is your real, and this is your imaginary. So one thing you've noticed is that, hey, if I divide a complex number with a complex number, I will always get a complex number. Unless your complex number for your denominator is 0, you should always get a complex number out of that. And that's a very, very important property in general. And remember, it might be a real number, but at the end of the day, a real number is a complex number. So that covers it for division. So we have all of our main operation. We know when two complex numbers are equal. We know how to add them. We know how to subtract them. I leave it as an exercise for you guys to figure that out. We know how to multiply them, which is kind of like foiling. And we know how to divide, which is just the idea of rationalizing. Now, I move on to, what is that? Some important stuff. How do we relate this to what we have been learning? Well, sometimes when we have a quadratic, I might have this. Let's say this is y equals x squared plus 1. Now, I've hinted towards this function, or a function similar to this, where, hey, our functions that we work with should always have the number of solution as our degree. It should. Or at least what we have been seeing, it has followed that case. But remember that another word for solutions is x-intercepts. This has no x-intercepts. So what's going on? Well, it turns out our x-axis is only showing real numbers. That's why. Now, unfortunately, you don't see it. You don't see the imaginary components. We create a different plane for that. It's called the Argon plane, or the imaginary real plane. But You can't really see it at the moment, but it does technically have an x-intercept. It's just your x-intercepts are imaginary. So, in this case right here, we have to know how to find our roots. It should have 2 roots at the end of the day. How do I find my roots? Well, if we remember how to solve a quadratic, solving quadratics, you have 3 main ways. Factoring is one of them. We have complete square, completing the square, and then we have quadratic formula. Right? And remember, when we're trying to solve for our solutions, roots, and x-intercepts, we're just going to set our function f of x equals x squared plus 1. We're going to set that equal to 0, our output. If I can solve for my input, then I can say f of something is going to be equal to 0, and that's a solution. That's an x-intercept. Remember that. Instead of p, I'm using the letter f this time. Well, how do we solve this? Because we can't factor this. I have not discussed how to factor, especially since you know it's an imaginary number. It is not going to be, a perfect square either, because difference of perfect squares uses subtraction. So, what we have to do is solve for x. We can just subtract 1 to both sides. You can complete the square as well. If you want to complete the square, you can. That is perfectly fine. You can also do quadratic formula. I'm just going to solve for x in this case. So I'm going to subtract 1 equals x squared, and I square root both sides. When I square it, I have to do a plus or minus. And then I get plus or minus square root of -1. X is equal to this. Well, we have a definition for square root of -1 now, if you guys remember. This is the exact same thing as saying x is equal to plus or minus I. Plus or minus I. So this is how we're going to be solving or getting our roots for any sort of polynomial if it has imaginary roots. We can set up in this math, and this is what I mean by it's algebraically complete. Earlier, there is no solution for this problem in particular when we were working with the real number system. But now that we're working with complex numbers, we will always have a solution. And that's very powerful. So, in particular, you're going to run through problems trying to solve these. Remember, you need to practice these 3, but you're going to run problems solving these, these quadratics or even these 5th degree polynomial if you struggle with these main topics. And then once you've done that, you need to figure out, you might have a square root such as, let's say, -50. How do I even calculate that? Well, the great side is we already know how to deal with problems like that. We can just deal with this as -1 times 50, which you can do the factor tree for 50, 10, 5, 5, 2, circle your pairs, and then you'll notice that definition of square root of -1 is I, and then you can pull out a 5, root 2. That's the idea how we can deal with square roots of a negative square roots now. We can actually factor out a -1 to our negative number, and then we have a definition for square root of -1, which is just I. And then you pull that out, and then you pull the other terms respectively. So, now before I even move on to anything further, I want to define what a conjugate is, because I think that's very important. Definition: a complex number, let's call it z equals a plus bi. I'm just giving the entire complex number a name called z. Right? A complex number, z is this, has conjugate, or they call this complex conjugate, I apologize. And the symbol for this is going to be z with the bar over it. If I put a z with the bar over it, we call that the complex conjugate. And that's just simply a minus bi. That's it. Alright, a minus bi. If your complex number is a plus bi, the complex conjugate is a minus bi. So you're just going to change the sign. If it was a minus bi, the complex conjugate would be a plus bi. All I'm doing is just changing the sign of my imaginary component, and that is it. Why is this important? Well, now we get into the meat of everything we've been talking about. I've already hinted towards this a lot, but this is called the fundamental theorem of algebra. Now, some books, they actually state the fundamental theorem of algebra differently from our book. And that's because they state the corollary. They state the results of the theorem itself. We're going to state the actual fundamental theorem of algebra, but I'm going to emphasize the corollary is probably more important. I'm not even going to say probably. It is more important for our class in particular. So, what does the fundamental theorem of algebra state? Every polynomial, let's call it P of x. And you know, we already know its form, of course. Has, with degree, I'm going to call it with degree. With degree n. So some natural number n, 1, 2, 3, whatever the highest exponent is, with complex coefficients. And remember, when I say complex coefficient, a real number is a complex number as well. So remember that. If I have real numbers, I can have a real whatever that I'm going to talk about. Has at least one complex 0/root. Has at least one complex root, which is, we've talked about, similar to x-intercepts in a way. If there was a complex x-intercept, if we could show what complex x-intercepts are, it would be there. Unfortunately, we can't. So it's going to be complex 0/root. What that means is that, hey, example, it's going to be very easy to just describe this. Oops, I think I froze. Draw. There we go. Example, let's say we have P of x equals 3x squared plus, we can even use complex numbers in our coefficients now. I'm not going to go into this idea though. I am not going to go into this idea, but I'm just going to show you briefly. That's for a complex course if you want to take that. But the idea is that, hey, this has degree n. These are all complex coefficients. There is at least one complex root. There is at least one complex root. Likewise, if I had instead changed this to, let's change this to -4, there's at least one complex root. Because remember, a real number is a complex number at the end of the day. So even though my root is real, it is still counted as a complex root. And we've already kind of had this idea. It's just now I'm giving you the actual theorem itself. This is a very powerful theorem, but the corollary is more important for this class. So when I go with the corollary, you do need to know this. Corollary. Corollary. The corollary I will tell you is that, what's that? I could just write it myself. I think I will. The degree of P of x is the number of complex. P is a polynomial, by the way, polynomial function. Number of complex roots. So, whatever my highest exponent is, that's how many roots I will have. That's how many zeros I will have. That's how many solutions I will have. That's how many x-intercepts I should have if I could plot down my complex x-intercept. So idea, P of x equals, let's say, I don't know, x to the 5th minus 3. Because my degree is 5, I have 5 complex roots. So that means you got to be able to find all 5 complex roots. And then we'll end it off with this one idea called the complete factorization theorem. the complete factorization theorem. What is the complete factorization theorem? Is if p of x is a polynomial function with a degree n bigger than or equal to 1, natural number, then there exists, oops, I'm not going to use that symbol, that's too much. And you guys already know this. There exists C1, comma, C2, comma, da, 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 all the way to Cn, a such that I'm just going to a does not equal 0, just to keep consistency, such that p of x is equal to a times x minus c1, x minus c2, x minus c3, all the way to x minus cn. There are n complex roots. If my degree is 5, I should have 5 of these. All it's saying is that I can write them as x minus that complex root times x minus that complex root times whatever. This a is just a real number. This represents vertical stretch. Vertical stretch, vertical compression or reflection, all of that good stuff. Reflection over x-axis, that's all it does. It has nothing to do with our root. So example, p of x could be, p of x is equal to negative 3 times, oops, let me do negative 3 times x minus 2, x plus 3, and then I'm going to do x minus 2i, x plus 2i. I can say that my complex roots are going to be, x equals positive 2, negative 3. This right here is positive 2i, and this right here is negative 2i. Because remember, it's x minus our value. Boom. I have my complex roots. There's 4 of them. Now, because there's 4 of them, well, let's give another example then. What happens if I have p of x equals, let's say, x times x, let's do x minus, minus 1 plus 2i, x minus 1 minus 2y. These parentheses here so I don't mess up. Right here. In this case, my complex roots are going to be x equals 0, x equals 1 plus 2y, and 1 minus 2y. Now, you'll notice something with these problems I did. Every time I listed a complex root, I always list its conjugate over here. That's very important. Every time you're going to be doing your factorization and whatnot, you will always, little remark, when solving for roots, if you have a complex number, a complex root, or I'm not going to say that, if you have a complex root with imaginary component, then the conjugate is also a root. The conjugate will also be a root. This is a very important thing. When you're solving for any roots, when you're solving an equation or whatever, or a function trying to find the roots, you will always, if you have a complex root, you will always have its complex conjugate. And it makes sense. This also applies for real numbers. It's just that the conjugate or the complex conjugate is itself, so we don't even write it down. But this is very important. Let's say I'm trying to solve for f of x equals x squared plus 9. If I want to find the roots here, I set my output equal to 0 x squared plus 9. Solve for x squared, subtract 9 equals x squared. Square root both sides, plus or minus. Then I'm automatically going to have x is equal to plus or minus 3i. I can turn square root of negative 9 equal to square root of negative 1 times 9. Then I can pull out an I. Remember, square root of negative 1 is I. And I can pull out 9. And this becomes plus or minus. And this becomes plus or minus 3i. Boom. So that means I have the complex conjugate with it. The first one is x equals positive 3i. And the second one is x equals negative 3i. These are conjugate pairs. So I think this is a good stopping point. We'll finish up 3.5 tomorrow or the day after that. And then we'll be good to go with 3.5. I will catch you guys later. Take care.